In this video, we talk about deformations in pressure vessels. Deformations are determined by strains. We call the fractional change in thickness E epsilon of t, and this is in the radial direction, but that's also the thickness direction, but it's going through the material that way. We call the fractional change in length epsilon sub L for a cylinder, that is the longitudinal direction strain. The fractional change in radius is the hardest to understand. Because radius is proportional to circumference, the fractional change in radius is the same as the fractional change in circumference. For that reason, we call the fractional change in circumference to be epsilon for a sphere, and epsilon sub c, that is the strain in the circumferential direction for the cylinder. So we can also refer then to the unstressed size with a subscript naught. So the length of the cylinder is L naught, the radius of a cylinder or a sphere are R naught, and the thickness is T naught. And then we have these strains that we just explained above, and so that means that the stressed size, which we will call L, R, and T, are the initial sizes times 1 plus the strain, as is the definition of strain. Now recall that the state of stress for the pressure vessels is always plane stress, and so that means we will need to use Hooke's law in 3D in order to find these strains. So that's all the information we need to go through an example. And so this example asks us to calculate the change in thickness of a spherical vessel when we're given the unstressed dimensions. R naught is 10 centimeters, T naught is 1 millimeter, and material properties E, Young's modulus is 2 gigapascal, Poisson ratio is 0.3, and it's exposed to a pressure 100 kilopascal. We are also asked here to think about whether it's okay that we have to use the unstressed thickness and not the stress thickness when we make these calculations. So we need to remember to return to that. So we learned in the previous video that for a spherical pressure vessel, all of the in-plane stress is PR over 2, and then in the thickness direction, we can assume the stress is essentially 0 because it is so much less. So we have the general form of Hooke's law in 3D, that is the strain in one direction is 1 over E times the stress in that direction minus the Poisson ratio divided by the Young's modulus times the stress in each of the other directions. And what we'll do here is use this to calculate the strain in the T direction. And keeping in mind that we have a tangent plane coordinate system that we can call x, y, and t, where x and y are any two directions in plane. The strain in the thickness direction is 1 over E times the stress in the thickness direction minus Poisson ratio divided by the Young's modulus times the other in-plane stresses, which are just the same, that is sigma, which are PR over 2T. So that means that the strain is 0 minus the same term twice, and that twice cancels the T here on the bottom, giving us that the strain is minus the Poisson ratio times PR over ET. And so we can then calculate that the change of thickness is just the thickness times that strain, and therefore minus T naught times V over PR times ET. That is, notice that we have the pressure divided by the Young's modulus, which are in pascals, and then the radius divided by the thickness, which are in meters, and so that whole phrase is a unitless term. Continuing with this example, so we had just calculated the change in thickness. And now we'll note that this derivation, we use the current values of R and T up here, not the original values of R and T. And that's because when we derived these, we were using the geometry of the pressure vessel under pressure. So in this case, though, we don't have the current values, so we're going to ask, can we use R naught and T naught? So we'll do a trick here that you can always use, which is that we'll go ahead and use them, but then we'll find out at the end what the strain is in this situation, which will tell us whether this was a good approximation or how good it is. So we'll say if the change in thickness now is minus T naught times the Poisson ratio times this ratio using the original values, now the T naughts cancel, and our change in thickness is minus Poisson ratio times the pressure over the Young's modulus times the initial radius. We just plug in the values that were given up here in the problem, and the change in thickness is minus that 0.3. We've now converted both the Young's modulus of 2 gigapascal into megapascal and the pressure of 100 kilopascal also into megapascals in order that it makes them easier to cancel. And we keep the 100, but we'll also turn that R into 100 millimeters because our thickness was in millimeters. And so this ends up giving us 0.3 times 0.005 millimeters, which is just a tiny little 1.5 microns. So that allows us to revisit whether it's okay that we use the initial rather than the actual thickness in these calculations. And we see that because T and T naught are only 0.15% difference, because this 0.15 micron was the difference relative to 1 millimeter. So then, because this answer is proportional to this inverse of the thickness, that when we put a 0.15% error in the thickness, it'll also give us about the same error in the change in thickness. And so our change in thickness is expected to be about 0.15% of 1.5 microns or 2.2 nanometers. And this is really okay because it didn't change delta T, that is the change of thickness within two significant figures that we were using in the first place. So this is generally the case with rigid, that is, materials that don't deform very much. In these cases, we can use the initial radius and thickness to do these calculations. So in summary, we've learned that we can use Laplace's law. And remember, Laplace's law are the set of values for spheres and cylinders. We can use them when the radius is much greater than the thickness. This is key. They must be thin-walled pressure vessels. We also can use them when we know the current geometry R and T, or when we know, so there's a big or here, or if we know the unstressed size R and T, and we determine that deformations are small, which can be done after actually using Laplace's law. And finally, we can also use Laplace's law when we know that the maximum strain is small before failure. That is, if the material is rigid and it simply doesn't stretch much, we know we can use Laplace's law to understand what the stresses are and when the material would fail. So this first one always has to be true, and any of these others, which allow us to know what geometry to use.